Hello, my name is Garrett Barker, and welcome to the virtual summit for the Hardware Checker for Probe Test Fixtures Capstone project. The technical directors on this project are Vicor employees Alfred Binder, Product Engineering Manager, and Nathan Shake, URI alumni of 2020 and Associate Test Engineer. Our consulting technical director is Mike Smith, a URI alumni of 2001 and the founder and principal designer of Bold Circuits, LLC. The team for this project comprises of two team members, Daniel Hartnett and myself, both majoring in electrical engineering. The company behind this project is Vicor, a Massachusetts-based company incorporated in 1981. Vicor is a leading global power and power module technology, selling their projects to the power systems market, high-performance computing, telecommunications, transportation, defense, and many more fields throughout the world. As for the economic impact of this project for the company, the hardware checker is anticipated to increase overall efficiency by reducing development time by 10% and reducing debug time by 50%, saving both company time and resources. The motivation behind this project is to expedite the internal and outside testing as well as troubleshooting of probe cards made for this company. The hardware checker can confirm the testing software being used works properly and detects hardware malfunctions. This will help manufacturers with troubleshooting and quality assurance of the cards. The anticipated best outcome for this project was to create tests for the P014, P013, and P037 probe cards, as well as test them in a lab environment for hardware functionality and correctness. The anticipated best outcome was achieved, and the P013, P014, and P037 tests were coded and applied to the corresponding probe cards. In addition, tests were coded for the needle checker as well as the probe interface checker projects in excess of the initial goals of the ABO. Here is a functional block diagram describing the general process of using a hardware checker. After setting up a probe card for testing, the resistor ring is attached to the card and the testing code compiled and run. If any components fail the test, the user will be alerted and debugging and part replacement can begin. If no components fail the first test, then the resistor ring is removed and another round of tests are run. Failures on these tests are debugged like the last one, and once no failures are detected, the card is correct and ready to use. The key accomplishments of the project have been the completion of the test code for the P014, P013, and P037 probe cards, as well as the lab tests conducted on the physical cards themselves with the completed code to ensure the test functioned as intended with no errors. Here we can see some of the components tested on the P014 probe card and the corresponding code created to carry out the tests. The schematic page on the left shows one of the P014 drivers in which voltage is forced and measured across the low and high pathways. On the right is the test of a pathway through various switches, switching those required to complete the path, then forcing and measuring voltage at the endpoint matrix pin to ensure the components along the path are correct. Here we can see one of the tests used to measure the value of a capacitor. The measurement is sampled in increments of ramping up and ramping down. The value of the capacitor is then calculated using the current multiplied by the time passed during the test divided by the voltage. On the bottom left is a demonstration of the ETS rate tool used to visualize the test results conducted on the capacitors. As mentioned in the block diagram, the test comprises of two rounds of tests, one with a resistor ring inserted and one with a grounding ring inserted. That is displayed here with the resistor ring and corresponding prompt displayed on the top and the grounding ring and its corresponding prompt displayed on the bottom. Now, my partner Daniel Hartnett will be speaking.
In addition to the multiple hardware checkers designed and tested during the first semester, a new project was added and completed called the needle checker. The needle checker is designed to verify all the pins on the PCB are soldered correctly and there is valid connection everywhere. Here is a functional block diagram of the needle checker, which can be better understood after hearing more about it in the coming slides. We also completed an additional bonus project called the probe interface checker. It's designed to verify all components and cables that come out of the interface board and get connected to the PCB. Here are two visuals of both the needle checker and probe interface checker boards after being built. For the needle checker, we started with an Excel sheet depicted in the left image, which mapped out all the pins on the board. We then were able to use the map to design tests that would verify the 1 k ohm resistance between each pin, making sure that if 1 volt were forced, that 1 milliamp was being measured between the pins. The capacitance tests were a little more in depth. In order to get the most accurate measurements, there needed to be a measurement taken while the circuit was open and then while closed. With both measurements, the open capacitance is subtracted from the closed value to get the actual capacitance of the specific pin. On the left is code sample of one test done on the open capacitance of pin 3 to pin 1. where the current is ramped just like how we tested for capacitance in previous hardware checkers. On the right is the sample code for how we were able to open and short the connectors holding the pins. Once the resistance tests and open capacitance tests were done, a pop-up display prompt will pause the test and inform the user to insert the shorting block to the corresponding connector that has the pins being tested on it. This shorting block shorts all the pins and allows for the capacitance measurements. Once all the connectors have been shorted, the test will be complete. The probe interface checker is an additional bonus project added on midway through the semester that was actually able to be completed. With more time, there probably could be improvements made to make the testing flow more efficient, but it currently does what it is intended to do. Here are two images of the board actually plugged into the tester. The gray cables and the timing cables as well as the voltage supplies all coming out of the interface board on the left image are what are being verified. The tests designed were based off the schematics that were given. On the left is sample code of how one of the matrices were verified and how it is connected on the schematic. Using a 1K ohm resistor, a 1 voltage is forced, and then a current measurement is taken, hoping for 1 milliamp. The same is done for the digital channels on the right. This is a sample of the first digital pin on the schematic. Here is an example of how the APUs were tested. The code shows APU 0 being tested, like the matrices and digital channels. The APUs are all connected to a 1K ohm resistor, and we force voltage and measure current. For the C bits, these are the relays being verified. There are 64 C bits divided into 4 banks, banks A through D. The code shown is a test designed to verify the first 16 C bits, bank A. The tester reads the C bit values in 2's complement, so with 64 C bits to verify, we found it easier if we could convert all the values for when the C bit is supposed to be on to display a 1, and to display a 0 for when it is off. Using a simple for loop, we created the test for all 4 banks, and on the right you can see we connected a couple APUs to the voltage supplies in order to verify every supply was working the way they should. By attaching an APU, we could force 0 current and put the APU on a higher voltage range like 30 volts and read the voltage measurement to make sure it is sending all 15 volts. This is the sample code for verifying the MPUs on the schematic. On an MPU, there is a high force, high sense, and a low force, low sense. To verify the MPU, we forced a 1 volt voltage to the low channel across a 1K ohm resistor and measured the current, hoping it would be 1 milliamp. On this slide are the test flow options for when running the test. For the first round of the testing, the components being tested were not on either connector SB1 or SB2, so we had a message display saying no connectors. That's what gets selected. Then for the second round, we are only testing the components that are on SB2, so only SB2 connected is what gets selected. And for the final one, only SB1 connected is selected. This project is considered a step-up test from the needle checker. If there is a failure when testing a PCB, having this test to verify the interface board is doing its job allows for easier debug. It eliminates the possibility that the interface board has a problem, which is one step closer to finding the solution. We would like to thank our technical directors Al Binder and Nathan Shake. They have been amazing mentors and supported us with every task we have been given. We would also like to thank our consulting TD Mike Smith. His expertise in PCB design is a very helpful tool to have by our side. And of course, none of this would be possible without Dr. Sunak, our Capstone program director. You continue to encourage our creativity and inspire us to work our hardest. Thank you.